Hey everybody, thanks for coming out. I'm super excited to be here. I'm super excited to talk about FHIR. I'm super excited to talk about the parts of FHIR that are great and the parts of FHIR that are hard. And what I'm here to talk about is how what the work we've done in an open source environment to try to make the parts of FHIR that are hard as good as the parts of FHIR that are good. So I've given this talk a couple of times in the past, and I think that I've come to the conclusion that I've been doing it wrong. And the reason I've been doing it wrong is because I'm a nerd, and because specifically I'm a FHIR nerd. And I know there are a lot of people that are probably like that in the audience, but the problem with that is it means that I tend to get into the weeds way too fast, and I immediately start talking about the most complicated parts of the spec, and I lose the forest for the trees. So this talk is going to be different. This is going to be less of a into the details and more of the overview of why this technology is powerful. And the reason I think I can do this is because we can officially announce that FHIR Proto 1.0 is released. And this means that this is coming with a lot more documentation than we used to have. So if the points I make are compelling, I can point you to all of this documentation. Now, I have to put an asterisk here, because just this morning we found a weird corner case in our FHIR path validation, so very, very soon 1.0 will be released. So, for the purpose of this talk, I want to talk about FHIR Proto as a format. So right now when you think about FHIR, you think about XML, you think about JSON. For the rest of this talk, I want you to bear with me here and think also of FHIR Proto as a format for FHIR, just like XML and just like JSON. And so if we want to talk about FHIR formats, we should talk a little bit about what the requirements of a FHIR format are. And these aren't something that is listed anywhere. This is just me coming up with what makes sense to me. I think a big one, it has to be an open standard. You don't want a proprietary format. You want something that anyone can read, anyone can write, anyone can handle, and there's an open community for working with this kind of thing. It needs to be language independent. We don't want to be talking about this is a Java way to write FHIR, this is a C++ way to write FHIR. It should be cross-platform, it should be language independent. It should be isomorphic with all other FHIR formats. This one is, this is a fancy way of saying the data is the same data no matter what format you put it in. It's all one-to-one. It's just a question of how you're looking at the data. So this is what you have to have in my opinion, in order to be a valid FHIR format. But we want to do more than that. What should a FHIR format have? Let's see, if you were thinking to yourself, what should a FHIR format have? What would you say? Here's what I would say. It should be easy to use. This means that no matter what part of the spec you're talking about, if it's, extensions, it's codable concepts, it's slicing, the format should make these things easy to use. This should be hard to misuse. There's a subtle distinction between these two, but I think it's really important. Hard to misuse means the format should make it so that it's hard for you to do the wrong thing. It's hard for you to get a code wrong. It's hard for you to get a date time wrong. It's hard for you to misformat an extension. It should make it easy to use and hard to misuse. It should be space efficient. This one, is a bit more technical, but if this is the way you're storing all of your data, you don't want it to be just overly expansive. And it should be strongly typed. This one is maybe you could call this a personal opinion. As a programmer, I'm a firm believer that everything on computers should be strongly typed. This is a little bit why our Python implementation's falling behind. And it should be smart. Now this is the bullet point I thought the most about, is how I wanted to phrase this. And what I came up with is that it should be smart. And it's not at all obvious what that means for a data format to be smart, but it's what most of this talk is going to be about. When I say smart, what I mean is that your data format should understand FHIR, and it should understand the FHIR spec. And that's what this talk is mostly going to be about, is how FHIR format understands what FHIR is, and makes that and uses that to make the data easier to work with. So why is this 1.0? This is 1.0 because we have stable, forwards compatible versions of the R4 protos. Now, I can't guarantee the spec won't change. For instance, 4.0.1 has more significant changes than you might expect over 4.0.0. What I can tell you is that our internal representation of any given version is now stable, binary, and forwards compatible. That means if you start writing with it today, tomorrow I'm not going to change the format on you. We have core library support. This means and the support varies across languages, and we'll get into that. But for the core functionality, we have a strong library support that makes it easier to work with this stuff. We have a user's guide, and that's cool. User's guide is fun because if you want to get into all the details, that's fine. What I think is even better is we have a great library of examples. And the nice thing about this is a repo that you can clone in and see how easy it is to set this up. It also gives you a script to generate a bunch of fake synthetic ND JSON and shows you exactly how to play with these records. And that's what a lot of this talk is going to be, is playing with records to show the benefits that you get. So what's a protocol buffer? I should probably mention this. Protocol buffers, my one-sentence line for them is protocol buffers are a language-agnostic way of defining strongly typed, space-efficient data structures. This means it's basically a struct that is language-independent and has all the backing of, this is internally everything that Google does is protos, right? So you've got the backbone of all the engineering of Jeff Dean and Sanjay and all of these really smart people that have been working to make this data format the best that it possibly can be. I'm going to talk a little bit about what it is, but I'm not going to go as in depth because this is the kind of thing that I used to dive into the weeds on, and I'm not going to this talk. So this is an example of a protocol buffer. This isn't a FHIR person. This is just an example of how you define a message. If you just look at that, it probably makes a lot of sense to you. There's nothing all that confusing. The only slightly confusing thing is why we have this equals number syntax. And what that is that's assigning a tag number to each field. And by assigning a tag number to each field, we can serialize in a very efficient way, because instead of having to store the name of the field and the type of the field and all these things, all we need is the tag number. And then we can look up, by checking the schema, the information on this. This allows us to be very space inefficient when we're serializing this to send it on disk or send it over the wire. And then what happens with that definition is that you can compile it into whatever language you want. And I do mean whatever language you want. Darn near every language that exists has a proto implementation, so you can take these records and compile it, and the serialization format is compatible. So that means you can serialize it in C++, deserialize it in Java, serialize it and deserialize it in Python or Ruby or whatever you want. And you get programmatic type-safe access to the code in all of these languages. So you see where I'm going with this, that we're starting to get to this idea of a strongly typed language that understands what it's trying to build. Everything can be serialized, the serialization is compatible across languages, and they can be sent over the wire, saved to disk. So that's what a proto is. Protos are cool, you can look up protos, but I'm here to talk about FHIR protos. Now, FHIR protos are proto definitions that are auto-generated by ingesting FHIR structure definitions, code systems, and value sets. So we take basically an implementation guide and turn it into custom protos based on the profiles and resources we're looking at. So what does this look like? You take all of these resources, you send them into proto-generate, and out pop a proto files for resource, code system, and value sets. So let's take a look at patient. If you spend much time looking at the spec, this is very familiar to you. We see a lot of fields. They're defined by data types. We see that gender here is a code. The code is bound to administrative gender. So let's take a look at what that generates in proto. We see here's our patient. We see all the same fields. Name, telecom, they're all typed to these data types which are defined elsewhere. Again, I'm not going to go too much in the details. If you look at this, it generally makes sense. But I do want to take a second to talk about the gender code here. We do have a primitive resource type for code, but there's more to this than code, because if we take a look at the spec, we know that the gender is bound to administrative gender. And FHIR proto understands this. And so what FHIR proto does, first we can take a look at what we do when we read the gender code system. When we read the administrative gender code system, we can understand what it's saying. What you're saying is these are the set of values that this thing can occupy. And so we make an enum. And then when we come into the patient proto, when we see this field, we understand, oh, that field has been bound to a gender code. We can therefore make a custom code that is bound to that enum, and boom, all of a sudden, it is impossible to assign an invalid code to this code system. And the reason is because FHIR proto is smart. This is probably the most basic example of how FHIR proto understands FHIR, but already you have an enormous class of errors that's eliminated, of incorrect codes bound in incorrect places. Okay, already I want to jump into an example. So as we've seen, you might have noticed that FHIR proto isn't really one-to-one with JSON, which is to say that it's isomorphic, meaning that everything that's in JSON has a corresponding way you can represent it in FHIR, but the fields aren't identical. And because the fields aren't identical, we need parsing and printing libraries to get back and forth. We need a way to ingest JSON and spit out FHIR proto and vice versa. So this is what the parsing and printing library does. So here's a clone of the examples library that I mentioned that we have. And so what I have on disk is a bunch of ND-JSON patients. You can generate these by using a script that's included in the library and play around with them yourself. It's pretty darn straightforward. We read the lines, for each line, parse it into a patient profile. And we'll say this is the patient we parsed. We're going to do this for 1,000 patients just to show you that it's pretty darn quick. So once we've parsed 1,000 patients, we're going to take one of them, print it out in proto form, and then just to show you what it looks like to manipulate some of the fields, we can show you how to access these fields in strongly typed ways. So okay, cool, let's go ahead. Workspace is just where I've stored. I swear I know how this works. So we parse all these patients. And then here's one in proto form. So you'll see it looks pretty familiar. You might guess what this looks like. It's cleaner than FHIR, but it still looks pretty much like FHIR. You see we have enums all over. We see that we can print out this string. We get nice access to these things. And the next thing we can see is that you can take that, this is a format, we can also print this to what's called analytic JSON. And if you've ever seen the stuff about analytic SQL on FHIR, this stuff is very easy to turn into a form that can be understood by BigQuery. I'm not going to go too much into the mechanics of that because it's all in the examples, but the bottom line is with a couple of lines extra, you can go ahead and turn this into something that you can query. So here's, for instance, I have the patients uploaded to BigQuery. You can run a real simple query, say select name and birth date from all of these patients that we uploaded, and this works just like SQL queries. If you've seen any of the other talks that talk about SQL on FHIR in greater detail, all of this applies to that because they use our analytic format. Great. So, but this is all well and good for all of these fields that are easily accessible, easily pokeable with SQL. But there's a lot more data in this, and I want to spend some more time thinking about that. Let's take a look at all of this data that is in extensions. There's a lot of data in this set that is in extensions, and it's all really reasonable data. It's all data that we feel like we should understand, right? Like let's take, for instance, the patient birthplace. This is a FHIR extension. This is not defined in some random corner by some random person. This is a FHIR well-defined extension. And yet, in order to query patient's birth city, imagine what your query would have to look like to iterate over to flatten all the extensions, find the extension that looks like birthplace, then grab the value, grab the address out of the value, the city, all of these things. If it's repeated, it's going to get even worse. The bottom line is it seems like this should be easy, because we understand the format and it's well defined by the structured definition. So let's take some more examples are these US core ones. These ones are defined by the US core spec. Again, a spec that should be known to us. So, FHIR gets a lot of its flexibility from unstructured data. Is the ability to have these extension key value pairs means anyone can define these implementation guides, and we can get data in ways that everyone can understand, but it's unstructured. And working with unstructured data is really hard. Just because of the fact that these are key value pairs instead of well-defined fields, it's tough to access them in code, and you can't query them. Now here's the key insight, is that profiles give us a map of what unstructured data looks like. All of a sudden, if you read the profile, it tells you how to build a structure to fit all of your data into it. So profiles tell you the kind of extensions to expect, they tell you the kind of codable concepts to expect, all these great things. So for instance, in the US core patient, we know that there should be a US core race, we know there should be an ethnicity, and we know there should be a birth sex. And we know what these look like because they're defined via these extensions. So we can use these profiles. FHIR-Proto understands FHIR. So FHIR-Proto understands profiles, it understands extensions. So we can use these profiles to generate even more structured data. So we can read that ethnicity extension definition. We read that ethnicity extension definition, and we generate a structure. The structure has an OMB coding. The OMB coding is bound to this particular code set that we also understand because we read the code systems involved in the US core. It has all these other fields. Basically, everything in that extension definition, we've ingested, we understand it, and we generate a custom data structure for it. And then we go ahead, and when we have our US core patient, we know to expect up to one of these ethnicity extensions. So way down at the bottom, we have all the normal fields for patient. I might have skipped it. I skipped it. There. Way down at the bottom of patient, we've made a field where that data structure that we just saw is plopped right into the proto itself. And why is this cool? This means that now we have the ability to take that patient data and convert it into the US core patient. So what this next example demonstrates is the ability to convert from data from one proto into another proto. So we take these patients and they say, you know what, this is a US core patient. Give me this data in the US core representation. So we're going to call it's going to do all that. It's going to parse them, and then it's going to print them. And what do we see now? All that difficult to understand data is now in normal first-class fields that's no different than any other fields. And now it's totally queryable, as we're going to see later on. And birth sex, for instance, is no longer a string. It's a code. Same with Hispanic or Latino, white. All of these things have been read from their unstructured data and converted into structured data. But that didn't get us all the way, did it? Because look, we still have that thing we talked about earlier. We still have patient birthplace. It's still a pain to work with. And the reason it's still a pain to work with is because US core profile doesn't tell you that it's there. We know it's there, but the US core doesn't tell you that it's there. Similarly, we notice that every time there's this marital status, marital status is a codable concept. Every time that shows up, there's a system with this marital status. We know it's there, but JSON doesn't know it's there, and US core doesn't know it's there. So how can we make it so that FHIR-Proto understands this? So the way we can... I skipped over a bunch of this. Okay, so the way we can do this is we can make our own custom protos, our own custom profiles that add this extra information. Now, there's all kinds of tooling out there that people have talked to you today about generating new profiles and new implementation guides, and those are great. And anything you generate with those will work with FHIR proto, because just like we can generate US core protos, we can generate protos based on any profiles you give us. You give us some profiles, you give us some codable concepts, we can generate. And there's examples in the examples directory about how you go about doing that, how you take an existing implementation guide and turn it into protos. But we also want to provide a simple end-to-end solution where just from our platform, you can also generate these things. So let's go back to what we were talking about. So the way you do this is what's called a profile config. And this is an example of a profile config. Profiles can extend from other profiles. We know that all of the US core things we saw that were really useful, we still want them. So what we're going to do is we're going to make a profile for a patient, and the base for this patient is the US core patient. So that means start off by saying everything that's in the US core, we want all of that. But we're going to add more. We're going to say, on top of that, we know that there's a patient birthplace extension, and we want to reject any record that doesn't have it, so we're going to go ahead and say that that's required. We know that on patient.marital status, there is always going to be a code system with this, or a code with this system. And let's stick with that for now. We'll save some for the next example. So what we've done is we've told it to add this additional information to a new proto, and we see that generated here. So here's our demo patient that was generated from that profile config, and what you're going to see is, in addition to the US core extensions, we also now have a birthplace extension that's typed as an address. And if we look at marital status, we see that we now have a new slice. This is confusing to look at in Proto, but it'll be obvious when I show it to you. But we've added a new slice to that codable concept. So let's go ahead and say, yeah, give me all those same patients, but this time, give me all those same patients in my custom profile. Now we see we've got this birthplace now that's accessible like any other data. It's an easy to read field, and on top of that, in this marital status, in addition to the normal codable concept field, we now have this v3 field, which means that we can say marital status.v3.code, and we're going to get the code that has that system without having to iterate through the codable concept. This also means, once again, that now all of a sudden that field is queryable because it's now a well-defined type instead of an abstract key-value pair. I want to point out one thing that's just kind of a fun detail, and that's that when you go through all of this, there's a handful of records that failed to get converted to the US core profile. So, and not many, it's about 3 or 4 on most runs, 3 or 4 that failed to convert. The reason why is because they use code 2131-0 for unknown. But the OMB race category value set requires you to use UNK for unknown. So the point here is that this is the exact kind of error that is impossible if you're using FHIR proto, because it is literally impossible to assign an incorrect code. The Cynthia people made a very easy to use mistake. They used a code that's invalid for that value set, and this is something that instantly gets caught by FHIR proto. Okay, so that's all well and good. We're going to go into a little bit more. You have some new kinds of data that doesn't fit into any extension that's already there. You want to add a new extension. So again, this goes back to the profile config. In this case, we're defining simple extensions and complex extensions. If you know, FHIR extensions generally come in 2 forms. A simple extension just has a value. a complex extension has no value, but it has many extensions. And in this way, you can encode arbitrarily complex data. So I'm going to show you examples of both of them. My examples are bad. It's because I'm not a very creative person, so you're going to have to bear with me here. My simple extension is a Boolean. It's likes pi. It indicates whether or not the patient likes pi. The complex extension is favorites. It encodes a structure that allows you to say the patient's favorite number, and then a pet name substructure that has favorite cat names and favorite dog names. You might argue that likes pie could be incorporated into favorites as some kind of favorites dessert, in which case you should go to the working group. So I've got a final example to tie together all of the things that I've been trying to talk about. So this is print to analytic ND-JSON. This is kind of tying together a lot of the concepts from the examples we've seen so far. What this is going to do is it's going to read directly into demo patients. It's going to then go ahead and populate all of these new extensions. So for instance, we can say mutable patient dot likes pi, set value true or false based on the value of some random number. We can say all these other fields. We can generate the favorite structure. On that favorite structure, add some pet names, some cat names, some dog names, and then at the end we're going to print this to JSON string for analytics. Now the difference between printing this to a raw FHIR JSON and printing it to analytics is when you print to analytics, you're doing it in a form that's designed for BigQuery, that's designed for SQL. And what that means is that whereas in FHIR JSON, FHIR JSON has no understanding of profiles, right? When you profile a field, the ultimate JSON format looks identical. And this means that it's not super helpful for querying. So printing for analytics is saying, I want to make use of this information. I want to make this information more useful to me, so keep that profiled field around. And printing to analytics also does a lot of other things, but that's the one I want to focus on for here. So yeah, let's go ahead and do that. Great. Now the next thing we're going to do is we have this new structure that we need to have some kind of understanding on. So we're going to generate a BigQuery schema for it. Okay, give me a BigQuery schema. It happens almost instantaneously. And then the last example I have on here is upload a resource. So, and what this is going to do is it's going to take that and upload it directly to BigQuery. So I'm just going to copy this here. The errors is just because it's writing to a table that already exists. And this is about 2,000 patients at this point, probably more actually because I've run this a couple of times to test it and generated more and more. But anywho, so now if we come over here to our BigQuery instance, we see our brand new table. I had a backup just in case something went screwy, but it doesn't look like I'm going to need that. So now let's think about some of these fields we've added. Let's select birthplace, favorite dot number. Is that it? Favorite dot favorite number. And well, let's just grab all of the favorites. What else did we add? And race. Sure. We see all the birthplace, favorite number, favorite pet name. The point is this is all just structures that we've invented on the spot and imposed on it, or structures that were invented by US Core, but FHIR Proto understands all of these. So this is the key. This is what I mean when I say that FHIR Proto is smart, is that instead of just being agnostic to the data it's representing, like JSON is agnostic to the data it represents, we understand not only the core resources, but profiles, we understand value sets, we understand code systems, and this way we can generate very customized data structures that make just about everything about working with this easier. Okay, great. So, yeah, I think I covered all that. We described the delta between the profile and the resource, feed it to a proto generation script. I'm glossing over a lot because it's all in the documentation. So coming soon to profile config, we got a lot of things coming down the pipe that we're excited about. We want to be able to generate custom code systems and value sets. This is a big one, and we know it's something we're missing. This is the last thing we need in order to say that you can generate a full implementation guide with our platform, is we're going to make ability to, in the similar way that you can just with the bare minimum number of lines, you can generate profiles, we want to do the same for code systems and value sets. Config validation. This one is an easy one, but it's one of these things that's always on your list and you never get a chance to bang it out and it just stays on your list forever. I'm going to write a simple validator that helps you get your profile config right and not have to futz with it too much. And GUIs. I would love to have a GUI for generating these things. Right now you do it by typing, which for people like me is great, but for some people it's easier to have something that you like move around and stuff like that. Okay, so we talked about what should a FHIR format have. It should be easy to use. I argue that FHIR Proto takes the hard parts about FHIR, the unstructured parts of FHIR, and makes it so that you can access them like any other field. It should be hard to misuse. I think this we cover by doing things like codes. You can't enter the wrong code. Once an extension is profiled, you can't. I remember once there was the QI core. I tried to ingest the QI core into FHIR Proto, and it just failed hard. And I was like, man, my system's buggy. It turned out that the examples in the QI core, they had an incorrect level of nesting in their extensions. So all of their extension data was not quite right. And these are the kind of things that you catch instantly when you use FHIR Proto. I think I've probably driven Graham up all kinds of walls because I'm always filing bugs where I say, you know, my validation fails on this resource in the spec and that resource in the spec. The bottom line is that because it's so structured, we catch validation failures that no one else catches. It forces your data to be correct. It's space efficient. You know, I wish I had the exact number. Every time I give this talk, I tell myself to get the exact comparison, but I gotta believe it's around 20-to-1 reduction in size over JSON because of the reducing codes to ints, reducing field names to ints, and just the sheer amount of work that's been put into making this the most efficient data structure possible. Which you know, this means a lot of things. This doesn't just mean you have fewer bytes on disk. It also means that your messages on the wire are a fraction of the size, and that's a big speed improvement, especially when you're thinking about things like bulk data. Strongly typed, this one's a no-brainer. You can't put an int in a decimal. You can put it in a decimal. You can't put a decimal in an int. You can't put the wrong kind of extension in the wrong place, et cetera, et cetera. And I hope that I've argued that it's smart. So that's all the good. Here's the ugly. The language support is not as far as I want it to be, but it's coming fast. We really wanted to get R4 in at least one format as perfect as possible, profiling as perfect as possible, rather than trying to develop all the languages at once. I'm a C++ guy. I focused on that. That's what we use mostly internally. So the C++ is the strongest of the four big pillars I think of in terms of language support. C++ is the strongest. Yellow means we're pretty far along the way. Yellow means that we're getting very close to releasing. To give you an example, the Go library is already totally written. It's just a matter of getting it into open source. And the next thing I'm going to be working on is the Java profiler. So all of this box is going to be done. I promise all of this box will be done soon. The yellow stuff is the stuff that'll be done first. So what's next? We want to build out tooling, because we now have this great platform where it's so programmatically easy to work with protos. It's what everyone at Google Health uses. It's what everyone in the cloud Google Health or cloud healthcare team uses is protos. Everyone uses protos because they're just a lot easier to work with. And so we think we can build a lot more great open source tooling that we can give to you guys and give to the community to make it easier for everyone to work with FHIR data. Some of this is going to be part of the FHIR library. Some of it is going to be external libraries that we release to work with it. Stay tuned. We got a lot of good stuff coming. Our goal is to make healthcare data easy to use with a wide range of popular tools, with data engineering, analysis, machine learning. So that's my talk. These are the GitHubs. If you get one thing out of this, it's github.com/Google/FHIR examples. I would love it if you could try them out, see how they work for you, and see what you think. I'm going to be doing a Let's Build tomorrow right around noon. I forget exact when, where if anyone wants to come and hack on proto-buffers with me, I'd love to hack on them with you. I hope I've made a case for FHIR Proto. Thanks for listening. Sure.
You said the language support is not there, but isn't once you generate the proto, aren't there like already client generating other libraries?
Absolutely. So just to, it's a very important point. You can use FHIR protos in every library, but they will be functioning mostly like just raw protos. So for instance, I didn't talk too much about our validation. We do an enormous amount of proto validation for things like FHIR path, required fields. All of those things aren't baked into the proto library. That's libraries we built on top of it. Things like parsing and printing. There's no way to take it. When I say parsing and printing, I hope I make this clear that what I'm talking about is moving back and forth between JSON and proto. I probably should just call that JSON and proto. Internally, we call it parsing and printing. I should just call it converting between JSON and proto. So there's no native proto-defined way to convert from raw JSON into a FHIR proto. That takes a library. So that's what I mean. But if you just want to work from scratch and use proto as your data model, yeah, you could do that in like Haskell, I'm sure. You could do it in anything because proto works on everything.
Can't you get a typed client if you do something like that?
Absolutely, yes. Yes, it's just what I mean is some of the fancier libraries that you'll find in github.com/Google/FHIR. The fancier libraries is stuff that I've written and released. And sometimes other people.